Faraday's iron filings experiment revealed the existence of an invisible field stretching out into thin air. These fields, he thought, were responsible for the experimental results he'd seen. Despite having physical proof, Faraday lacked a mathematical description of how the field was generated, or why it affected things around it. Without a mathematical proof, many 19th century scientists dismissed the theory as speculative. But Maxwell had followed Faraday's work for years and set out to prove him right. His aim was to provide a mathematical explanation for the link between the two. After years of thinking, and who knows how many miles walking, he came up with a set of equations that described the relationship between electricity and magnetism. Equations that would change our lives forever.
Sorry, Frank, but this is just gobbledygook to me. I'm just looking at it, trying to make sense of it.
Well, it's not much easier for me. I mean,
Oh, no.
that's what he wrote first of all, and looking at these, they probably mean little more to me than to you. But 20 years later, they were written in a simpler form, which is the way that
This right here.
this
That looks-
form here.
That looks more manageable, but it still looks a bit confused. Could you take us through it then?
Right, well, the first one says that if you've got an electric charge, it spreads an electric field out all over space.
Just like his work on Saturn's rings, each equation is a mathematical description of something observed in the real world. So the first equation described how a static electric charge generates an electric field. And the second, that magnetic poles always come in pairs. The third equation describes how a changing magnetic field generates an electric field. And the fourth equation, that an electric current surrounds itself with a magnetic field. But Maxwell realized there was something missing.
Maxwell's genius was to realize that each of these equations is fine until you put them together.
Mm-hmm.
And then he realized something was missing, and it was in this final equation. He said, there has to be another term. And what this extra piece says is if an electric field is changing, it will surround itself with a magnetic field.
Right.
Which is like the sort of mirror of this equation, which says if a magnetic field is changing, it will surround itself with an electric field. So just take these two together and just think about it for a second. If I've got a magnetic field changing, it surrounds itself with an electric.
Yeah.
If the electric is changing, it surrounds itself with a magnetic. And if that is changing, it will surround itself again with an electric, and so on. Faraday to Maxwell, electric to magnetic, back and forth, back
So
and
there's a
forth.
coupling basically between the two.
Maxwell's equations were saying that electric and magnetic fields were inextricably linked. Changes in one created changes in the other. It helped explain so much. When Faraday moved these magnets, he changed the position of the magnetic field, and this triggered an electric field which caused electricity to flow through the wire. And when electricity passed through a wire, it wrapped a magnetic field around it, causing the compass needle to move. Using pure maths, Maxwell had unified electricity and magnetism, and shown there were two aspects of the same thing, a single electromagnetic field. This alone would have guaranteed Maxwell's entry to the Scientist Hall of Fame. He could have rested on his laurels. But whether it was his natural curiosity or the long walks with Toby, he didn't stop there. He used his equations to test another of Faraday's ideas. Faraday had guessed that under certain circumstances, the electric and magnetic field lines could be disturbed by waves travelling along them, almost like ripples on the surface of water. Maxwell used his equations to show that the fields could fluctuate in time with each other, and cause what Maxwell called an electromagnetic wave. He could even measure the speed of the wave.
This says the electromagnetic wave travels through space, and buried in here, he was able to extract the speed that the wave travels. And when he put the numbers in from things that Faraday and others had already measured, he worked out the speed, and it came out as a phenomenal 300,000 kilometers every second, roughly. And that, I think, is the moment of discovery, because he knew that people had measured the speed of light, which was 300,000 kilometers every second. Now, at this moment, you think, is this a coincidence? Or are these equations telling me something?
Yeah.
And, of course, they're telling you something. And what the message is, light is an electromagnetic wave.
This was a stunning conclusion. Maxwell had explained what light itself was. At the same time, he'd introduced something new to science: electromagnetic waves. And they were destined to change our planet. The problem was, he hadn't physically demonstrated the existence of these waves. It was all in the maths. Physical proof would have to come later. His equations were an astonishing piece of work, packed with radical ideas.
Maxwell gave us a unified theory of electricity and magnetism. He solved the mystery of what light was, and he predicted the existence of these invisible fields that would directly affect our life. You know, that's difficult enough to grasp for a 21st century scientist, but what on earth did the Victorians think?
The fact is, Maxwell was asking a lot from his peers. Invisible fields, undetected waves, dense maths. It's all a bit much for 19th century scientists. Ironically, Maxwell found himself in a similar position to Faraday, surrounded by sceptical colleagues and lacking the proof to vindicate his theory. But a jubilant Maxwell was undeterred. He wrote an excited letter to his cousin.
I also have a paper afloat with an electromagnetic theory of light, which until I'm convinced of the contrary, I hold to be great guns.
The guns may have fired, but it would be a while before they'd be heard. It took more than 20 years before a German scientist called Heinrich Hertz found physical proof for electromagnetic waves. When he was asked what practical use the wave had, he replied, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right." How wrong he was, because Hertz had discovered radio waves. Marconi invented the radio, and since then we've been using them to spread radio and television all over the planet. But this was just the first in a long list of discoveries.
Happy days are here again.
Using higher frequency radio waves, we developed radar, which now gets used in everything from aviation to geology. Microwaves were discovered, which we use in cooking and when we use a mobile phone. Infrared is used in thermal imaging and in most TV remote controls. Ultraviolet is used in fluorescent lamps, security marking and medical research. X-rays have provided us with a valuable medical tool, but more recently in security. And gamma rays have been used to detect and treat cancer, and even to sterilize the food we eat. All these things are connected. Maxwell had shown that light and the colours we see are electromagnetic waves, but he predicted there would be more. Today we know that visible light is just a tiny sliver of a broad spectrum of electromagnetic waves. And by understanding and exploiting them, we've revolutionized our world. All thanks to equations Maxwell published 150 years ago. But focusing on the technological results of his work diminishes its importance, because he changed the way we understand reality itself.
Before the work,
Maxwell is all around us. Every single piece of technology that's around us today, computing, fiber optics, cameras, mobile phones, everything depends on extensions of those Maxwell's equations. Without those, we wouldn't be where we are today. Even the internet doesn't exist without those. Maxwell changed the way we think forever.